You know, when you think about a massive building, the air conditioning system is basically its circulatory system. And right at the very center of it all, you've got this powerful, unsung hero, the chilled water pump. Today, we're going to engineer one from the ground up and really see how it acts as the beating heart that keeps everything cool and comfortable.
So, have you ever wondered how you actually cool the top floor of a skyscraper? Or maybe a huge, sprawling hospital? Well, the secret isn't just about blowing air around. No, it's all about engineering the incredible journey of water. Let's follow that journey and see exactly how it's done. So, at its core, this whole system is really just one big, continuous loop. The chilled water pumps are the muscle, the engine that pushes cold water from a central chiller plant all the way out to the equipment that cools the air. We're talking about those big air handling units, or AHUs, and the smaller fan coil units, FCUs. The pump's job is actually pretty simple. Push the cold water out, let it absorb the heat, and then bring that warm water right back to get chilled all over again.
Now, to be really smart and efficient about this, engineers often use a clever trick. They split the job between two sets of pumps. You've got the primary pump, which is all about stability. It keeps a nice, constant flow of water moving through the chiller, because that's how chillers like to operate. But then you have the secondary pump. This is the smart one. It actually changes its speed, varying its flow to perfectly match whatever the building's cooling demand is at that exact moment. This simple split saves a ton of energy.
Okay, so the very first question an engineer has to tackle is, how much water do we actually need to move? This is our flow rate, and we measure it in gallons per minute, or GPM. To figure it out, we use this absolutely fundamental formula. It connects the building's total cooling needs, that's the BTUs, with the temperature difference between the supply and return water, which is what we call the ΔT. If you know those two things, this formula tells you exactly how many gallons per minute you need to be pumping.
Of course, pushing all that water around isn't a walk in the park. The pump has to fight against resistance through, sometimes miles of pipe. So the real core of the design process is adding up every little bit of that resistance. And in engineering, we have a name for that total resistance. It's called pump head. Pump head is basically the total amount of oomph the pump needs to generate to shove that water through the entire system, overcoming all that resistance. Think of it like this. Engineers measure this push in feet. It's like saying the pump has to work as hard as it would to lift a column of water that many feet straight up into the air. This single number, this is our target.
So where does all this resistance come from? Well, it boils down to three main culprits. First, you've got friction from the water literally rubbing against the inside walls of the pipes. Second, you get turbulence and more friction from every single bend, T, and valve in the system. And third, there's a big pressure drop when you force the water through the tight, dense coils inside the cooling units themselves. And because this is a closed loop, static head is zero. We don't have to worry about lifting the water to a higher elevation. And just to give you a feel for what we're talking about, in a pretty standard system, just the pipe friction alone can add up to 25 to 40 feet of head. Then you toss in the resistance from all the fittings and the pressure drop across the cooling coils, you can see how fast that total pressure requirement, the total head, really starts to build up.
All right, so check this out. We now have the two critical pieces of our puzzle. We know how much water to move, that's our GPM, and we know how hard we need to push it, that's our head. With just those two values, we can finally figure out just how powerful our pump's motor needs to be. We can calculate the horsepower. And this right here, this is the magic formula that brings it all together. It's the bridge that connects the system's water needs with the raw mechanical power we need from the motor. It takes our flow and our head and spits out the horsepower required. It's that direct.
Let's just quickly break this down. We've got our GPM and head. We just figured those out. The specific gravity for water is just 1.0, so that's easy. The last piece is eta. That's the Greek letter for the pump's efficiency. You see, no pump is 100% perfect. Some energy always gets lost. So this efficiency value, usually somewhere between 70 and 85%, just accounts for that real-world energy loss.
Okay, that's enough theory. Let's be honest, the best way to really get this is to just walk through a real example step by step. We're going to take everything we've talked about and put it all together to size a pump for a project right now.
First things first, we've got to calculate our total head. So for this example, let's say a detailed analysis tells us our pipe friction adds up to 35 feet of head. All those little elbows and valves, they contribute another 10 feet. And finally, the manufacturer's data for the main cooling coil says we're going to lose 20 feet of pressure pushing water through it.
So you add those all up, 35 plus 10 plus 20, and boom, 65 feet.
That is our magic number. That's our total dynamic head. It is the one single target our pump has to be able to hit to do its job right.
Okay, we're on the home stretch. Let's say this particular system needs a flow rate of 360 GPM to keep everyone cool. We've got our flow, we've got our head. Time to plug them into that horsepower formula and see what we get.
So you run the numbers through the formula, and it comes out to about 7.9 horsepower. Now here's the thing, you can't just go out and buy a 7.9 horsepower motor. So what an engineer does is they look at this and select the next standard motor size up, which in this case would almost certainly be a 10 horsepower motor.
All right, so we've sized our pump, it's ready to go. Its job now is to deliver that precise flow of chilled water to the equipment that's actually going to interact with the air that we feel. This is where all that hard work pays off.
The main workhorse for cooling in a big space is usually an air handling unit, or AHU. It's basically just a big box that uses our chilled water to cool down a massive amount of air. But here's the key thing to see. It's how it all connects. Remember that coil pressure drop we used in our calculation? We had to get that number from the AHU manufacturer before we could even size our pump. Every single component in the system depends on the others.
And for smaller, individual rooms or zones, we use these little guys, fan coil units, or FCUs. They work on the exact same principle, just on a much smaller scale. Each one needs a very specific GPM to handle its room's cooling load, and we use little balancing valves to make sure every single FCU gets the exact flow it needs, no more, no less.
You know, there's a quote that I think just perfectly captures the elegance of this whole design. A chilled water pump isn't just some brute force machine. It's a precision instrument. Its entire purpose is to deliver energy in the form of cold water to the exact spots that need it, at the exact rate they need it.
And really, that's the ultimate takeaway here. If you undersize the pump, the building just won't get cool enough on a hot day and people will be miserable. If you oversize it, sure, it'll work, but you'll be wasting a shocking amount of electricity 24/7 for the entire life of that building. Getting it just right, that's everything.
So the next time you walk into a nice, cool office building or an airport on a sweltering day, just take a second. You might just find yourself thinking about that powerful, perfectly engineered heart, hidden away in some mechanical room, tirelessly pushing water on its invisible journey, all just to bring you a little bit of comfort.